screen. Okay. Can you all see my screen now?
Yes, ma'am.
Okay. Okay, so today is our second online class. We had a LMS class last week, and we will straight away, I won't go into the recapitulation of last class because that itself was a revision class for you, because those were all included in your +2 syllabus. So I won't go into recapitulation, although from next class onwards, before beginning the topic of that class itself, I will recapitulate the topics that I have done in the previous classes, but not today because that itself was a revision for you. So we will straight away move on to vector multiplication. Now vector multiplication, once again, is something that you have done in your 11 and 12 syllabus, in I think your mathematics as well as your physics portions. And as you know, that vector multiplication is of two types. The first type being the scalar or the dot product. And from the name itself, you can understand that the result of this kind of multiplication is a scalar quantity. The result is not a vector. So when you multiply two vectors using the dot product, the result that you get is a scalar. Okay. So suppose you have a vector A like this, and you have another vector B like this, and from our previous classes discussion, you know that wherever be the positions of A and B, by parallel displacement, you can always bring them together in this manner. So suppose you are asked to take the product of two vectors A and B. So what you do is you simply bring them together by parallel displacement and place them in this manner to perform the product of the two vectors. And suppose the angle between these two vectors is theta. Okay. So by definition, the dot product A dot B is equal to C, where C is a scalar, right? And what is the value of that scalar? It is given by magnitude of A multiplied by magnitude of B multiplied by cosine of the angle theta between them. Okay, so this is the formula or the mathematical definition of the dot product of two vectors. Okay, as you can see from the definition itself that the result does not contain a vector, so the result is a scalar. Why the result is a scalar physically, that we will also get to know very soon. Of course, from this formula, it follows that if the angle between two vectors is 0, that is, if you are talking about two vectors that are parallel to each other, then A dot B is equal to just the product of the magnitudes of the two vectors. Correct? Please do not think anything about this oppositely oriented arrow over here. It is a typing mistake. So if the two vectors are parallel to each other, then from the definition of dot product, it follows that A dot B is equal to simply the product of the magnitudes of the two vectors. And on the other hand, if two vectors are perpendicular to each other, then once again from the definition of dot product, it follows that the dot product in that case is equal to 0. So suppose you are given two vectors and you are asked to comment whether they are parallel to each other or not, or suppose you are simply given two vectors and you are asked to comment on the angle between them, then you can simply take the dot product and say that if the dot product is 0, then you can quickly say that the two vectors are perpendicular to each other. If the dot product is the product of the magnitudes of the two vectors, then you can quickly say that the two vectors are parallel to each other. And for any value in between, you can say that there is a certain angle between the two given vectors. Okay, so from the simple formula, you can comment about the orientation of the mutual orientation of two given vectors. All right. So from this definition, if one of the vectors is A and the other vector is, suppose, I cap, the unit vector along the x-axis, so then if you take the dot product of the vector A with I cap, the unit vector along x-axis, then according to the definition of dot product, we will get mod A into mod I into cos alpha, where alpha, remember, is the angle made by the vector with the x-axis. But mod I is 1. And if you remember the definition of direction cosines, then we defined A cos alpha is equal to AX. That is the x component of A along the direction of the x coordinate. Okay, if you remember how we defined components in our last class. So A dot I gives you Ax. Similarly, A dot J will give you AY. A dot K will give you AZ. So from this, we can see that there is a significance of the dot product, that is the projection of a vector. Taking the dot product is simple, in simple language, means taking the projection of one vector on another. And that is why we get a scalar. Okay, so when you take the projection of one vector on another, there is no question of a direction, and that is why we get the result as a scalar. And from here, this short calculation, you can see that the projection of a vector onto a coordinate axis gives the Cartesian component along that particular axis. Okay, so this is another way of looking at the components of a vector. What are the components? The components are nothing but the projection of a vector along that particular coordinate axis. Okay, so from the definition of dot product, we get this point of view about the components of a given vector. Okay, now once we know this way of writing down, we can see that suppose you are writing the dot product of two vectors A and B, then what we do is we write the vector B in component form. Okay, I expand B in the component form as bx x cap plus by y cap plus bz z cap. So since bx, by and bz are scalars, we take them outside and we write this as bx into a dot x cap plus by into a dot y cap plus bz into a dot z cap. And we know that a dot x cap is nothing but ax, a dot y cap is nothing but ay, a dot z cap is nothing but az. We just now defined the components in that manner, and I hope you are not confused about why I have written I, j, k and x, y, z caps. Both mean the same. The meaning of I cap, j cap and k cap and x cap, y cap and z cap are the same. They are the unit vectors along the three coordinate axis. So since this is the components are defined in this manner, we can write this expression as bxax plus byay plus bzaz. And these are all scalars, so the position does not matter. You can as well write ax bx, ay by and az bz because the components are just scalars. So in component notation, the dot product can be written as the sum of the products of the components of the vectors. Okay, so summation ai bi, where I goes from x through z, or summation bi ai, where I goes from x through z. So A dot B and B dot A are the same, and this is the dot product written in the component form. So for dot product, you have to remember these two expressions. Both ways of writing the dot product are correct. Both ways are in use, and we will be seeing that when doing a problem, we will require both the expressions. A dot B equal to AB cos theta if you know the angle between them. A dot B equal to ax bx plus ay by plus az bz if you know the component form. So both the formulae are required to be remembered. Okay. Next, from the definition of the dot product, we can now write that since x cap and x cap, of course there is no angle between them, so x cap dot x cap, y cap dot y cap and z cap dot z cap are all equal to 1. Whereas since the coordinate axes are mutually orthogonal, therefore x cap dot y cap equal to x cap dot z cap equal to y cap dot z cap equal to 0. So the dot product of the unit vectors amongst themselves is 0, whereas the dot product of the unit vectors with themselves is equal to 1. This again shows that the unit vectors are perpendicular to each other. Example of dot product. Again, this is recapitulation of schoolwork. Work done, F dot S, where F is the force and S is the displacement that the particular force produced. And we know that if the direction of the force and the displacement that it produces in the body are same, then the work done is maximum. Whereas if the force is acting in such a manner that the body is displaced perpendicular to the direction of action of the force, then the work done is 0. And from here you get the concept of no work forces. So no matter how much force you apply on a body, if the body moves in a direction perpendicular to the direction of action of the force, then no work is done, and that comes from the definition of dot product. Correct? Another very important concept, I don't know whether you have done this, comes from the realm of coordinate geometry. Okay, dot product gives us the normal to a given plane. How? Suppose we have a vector r, x cap plus y cap. Okay, x can have any value, y can have any value. So basically this vector r is a vector in the xy plane. All right, this is what I'm talking about. You have the xy plane and we have a vector r in that xy plane. The orientation of r can be anything depending on the values of x and y. Only restriction is that it is confined to the xy plane. Okay, now if we have another vector, a unit vector called n cap, such that n cap dot r is 0 for all r. From the expression of r, you can see that r is variable, right? It depends on the values of x and y. But if n cap is a unit vector such that n cap dot r equal to 0 always for whatever value of r you have, then we say that n cap is perpendicular to the entire xy plane. Okay, this is what I mean. If you have a vector n cap such that n cap dot r equal to 0 for all r, then we can say in general that n cap is a vector that is perpendicular to the entire xy plane. Clear? So in this manner, using the dot product, you can find the normal to a given plane. How will you find the normal to a given plane? If you are given a vector, say, and you are asked to determine whether it is the normal to a given plane, then you take a vector in the given plane, you take the unit vector along the given vector, take the dot product of the two. If the dot product comes out to be 0, then you can safely say that yes, this is a normal to the given plane. If the dot product is non-zero, then you can safely say that no, this is not a normal to the given plane. Is this clear to everybody? Okay. So I'll move over to my next slide. The other kind of multiplication, that is vector or cross product. So we saw that when we take the dot product of two vectors, the result is a scalar. And the other type of vector multiplication is the cross product, which is also called the vector product because the result is a vector. Okay. So by definition, this is how we write a cross product, A cross B equal to C, where C is a vector. How do we get C? C is assigned a direction which is perpendicular to the plane of A and B. So C is a vector which is perpendicular to both A and B. Now when you have two vectors, then you can pass a particular plane through the two vectors. Suppose you have a single vector, okay? How many planes can you pass through a single vector? Can someone unmute and tell me? How many planes can you pass through a single vector? Can someone unmute and tell me?
Madam, one plane?
Through a single vector?
Yes.
Anyone else? Okay, suppose you have one dot, okay, one point in place. How many lines can you pass through one point in space?
Infinite.
Infinite number of lines. How many lines can you pass through 2 points in space? Suppose you have 2 points. How many lines can you pass through them?
One.
One line. So the moment you have another point, you from infinite you come down to 1. So if you have one vector, how many planes can you pass through it?
Infinite.
Infinite number of planes. It can be any orientation. The plane can have any orientation and still contain a particular vector. But the moment you have two vectors, how many planes can you pass through it?
One.
One. So just this in the same manner as we discussed the points, the same is happening with the vectors. The moment you have two vectors, then you can pass only one plane through that vector. And when you are defining cross product, the resultant vector of crossing two vectors is a vector that is perpendicular to both A and B. Therefore, it is perpendicular to the plane containing A and B. Okay, that is how we define the orientation of the vector that we get by the cross product of two vectors. A, B and C, where A and B you are crossing and C is the result of that cross, they form a right-handed system. What does that mean? It means that A cross B equal to C, B cross C equal to A, C cross A equal to B. Okay? A, B, C forms a right-handed system. It means that A cross B equal to C, B cross C equal to A, C cross A equal to B. On the other hand, since they form a right-handed system, therefore B cross A will be minus C, C cross B will be minus A, and C cross A will be minus B. So unlike the dot product, where if you interchange the positions of A and B, the result does not change because it is a scalar. In case of cross product, the position of the vector when you are crossing them is relevant. So if you take A cross B, you get C, whereas if you take B cross A, you will get minus C, and so on and so forth. All right, that is the meaning of the right-handed system. So if you have a vector A like this and a vector B like this, and the angle between them is theta as earlier, then this is the definition of the magnitude of the dot product. Okay, magnitude of A cross B is magnitude of A multiplied by magnitude of B into sine of the angle theta between A and B. Okay, A, B, sine theta. So in dot product you get AB cos theta, in cross product you get AB sine theta. And of course, therefore, if the angle between them is 0, then A cross B is 0 because sine 0 is 0. So as you can see, x cross x equal to y cross y equal to z cross z equal to 0. Whereas if the angle between them is 90 degree, then you get the magnitude as the product of the magnitude of the two vectors. Also, x cross y will give you z, y cross z will give you x, and z cross x will give you y. And just as I told you, they form a right-handed system. Therefore, y cross x will give you minus z, z cross y will give you minus x, and x cross z will give you minus y. Okay, so these are small facts which you must be knowing, but I just thought that mentioning these will be good for you because these are important things that we sometimes slip our memory. In component notation, A cross B is written like this. So in the component notation, if you are given the vectors A and B in component form, then this is the cross product, how you obtain the cross product. You take a determinant. First row will be the unit vectors I, j and k. Second row will be the components of the first vector A, and third row will be the components of the second vector B. I hope all of you know how to calculate a determinant. So from this formula, you can get the component form of the vector C, and also given the direction I cap, j cap and k cap, you can get the direction. And remember, as I told you, that the vector C is perpendicular to both A and B. So if you are given two vectors A and B, you can take its cross product, and then you can take the dot product of C individually with A and B to show that indeed C is perpendicular to both A and B. Because if you take the dot product of C individually with A and B, in both cases you will get 0, because the dot product of two perpendicular vectors is always 0. All right? Okay. So these are the two formulae that you need to remember in case of a cross product. In case of a dot product, I gave you two formulae, one in terms of the angle and the other in terms of the component. Similarly, in case of cross product, you have these two formulae, one in terms of the angle and the other in terms of the components. Okay. Now that we know dot product and cross product, which involved two vectors each, we will discuss the other kind of vector multiplication. Of course, you can take n number of vectors and multiply using a combination of dot and cross. But relevant for us, for the things that we are going to study, is the triple product of a vector. And triple product can again be of two kinds. The first one is the scalar triple product, where the formula is given by this: A dot B cross C, or B dot C cross A, or C dot A cross B. Okay, so it is a combination of dot and cross, but since you are crossing two vectors and then dotting it with another, the result of course is a scalar. Clear? So what does it mean? What is the geometrical significance of a triple product? Suppose these are the three vectors. Okay, in my Cartesian coordinate system, I have the three vectors A, B and C, randomly oriented. I have chosen one particular orientation of A, B and C in the three-dimensional space. So B cross C, from the first term, we have within the bracket B cross C, and we know from our just learned definition of dot product that B cross C, the magnitude, I'm sorry, I should have given a modulus over here, modulus of B cross C is BC sine theta, where theta is the angle between B and C. Just a second. There should be another slide. Just a second. I have missed one slide. I did not, I skipped the slide on geometrical interpretation of cross product. I discussed about, sorry. Okay, so I gave you the three formulae of cross product. Next, let us discuss the geometrical interpretation of cross product. Just as I told you, the geometrical interpretation of dot product is the projection of one vector onto another. The geometrical interpretation of cross product is given when you follow this figure. Okay, so in this figure we can see a parallelogram PQRS where the sides PQ and PS are formed by the vectors B and A respectively. Okay, so in this parallelogram PQRS, B sine theta is the height, correct? If you look at this picture, then B sine theta is nothing but the height of this parallelogram. Okay, so in the formula of dot product, which gives you magnitude of A multiplied by magnitude of B into sine theta, so here B sine theta is the height and magnitude of A will give you the base, right? So this is nothing but height into base, which means it is the area of the parallelogram. So the magnitude of the dot product of two vectors is nothing but the area of the parallelogram of which two sides are formed by the given vector. Okay? And the direction is given by the vector, remember, normal to both A and B. So normal to the plane containing A and B, which means it is normal to the plane of the parallelogram. All right. So the significance, geometrical significance, a geometrical interpretation of the cross product is that the cross product of two vectors gives you a vector that is perpendicular to the plane and in magnitude, that is giving the area of the parallelogram formed by the two vectors. The parallelogram, the sides of which are formed by the two vectors. All right. This concept we will be using several times in our later discussions. The concept that area can be treated as a vector. You can see that area, any given area, it's a parallelogram, but any given area you can think of, if you take an area and start, dividing it into small segments. Suppose you have any arbitrarily shaped area, you just draw a grid. All of you know what a grid is. All of you take photographs on a mobile phone and you know how a mobile phone offers you a grid when you try to take a photograph. And if any of you is interested in photography, then you must be knowing what a grid is. So any given arbitrarily shaped area can be divided up into segments by a grid, right? Horizontal and vertical lines. And each segment of this grid is a small rectangle, which in turn is a parallelogram. And we can see that any parallelogram is formed by the cross product of two vectors. So cross product of two vectors gives the area of a parallelogram, and therefore the normal to this parallelogram is the direction of that particular area. So now you can treat an area as a vector. So long we assigned a direction only to line segments. We thought of areas as scalars. Now that you have the geometrical interpretation of a cross product, you can now treat an area as a vector. Okay. So in my future classes of vector differentiation, integration, etc. Whenever I refer to area as a vector, whenever I assign a vector sign to a given area, please recall this class. We can assign a vector sign to a given area because of this concept of cross product. Okay, is this clear to everybody? Is there any confusion regarding this? Okay, if not, then I'll move to the next slide. Has everybody understood why we can assign an area with a vector? Yes?
Yes, ma'am.
Okay. So we were talking about the scalar triple product, and so now B cross C is BC sine theta, which is a parallelogram. We just saw that BC sine theta, the magnitude of the cross product, is nothing but the area of a parallelogram. So which parallelogram is this? This parallelogram, right? The sides formed by B and C. So if you take the cross product of B and C, then you get the area of this parallelogram. And the direction is given by a vector normal to this plane containing B and C. Okay, so this might be wrong. My drawing might not be exactly perpendicular, but you at least get a feeling of what I'm trying to say. So B cross C is a vector perpendicular to the parallelogram containing B and C. So when you take the dot product of A with B cross C, basically you are taking a projection of this vector onto this B cross C. All right, and that gives you the height, right? Multiplying the base area with the projection of the vector A onto the normal. B cross C is the normal. So it is nothing but the height. Taking the projection of A onto B cross C will give you nothing but the height. So height into base. What does it give you? What is the result of
Area.
multiplying, not area, height into base? Base is
Area of
area.
triangle.
Height into base. Base here is the area. This is the base.
Perpendicular.
Ma'am, volume.
Volume. Right.
Volume, ma'am.
Height into base. Here the base is this area. Please try to understand. This is the area, B cross C. Okay. Its direction is this, B cross C, normal. When you are taking dot product of A with B cross C, basically you are multiplying it with the magnitude of this area, and you are getting the projection of A onto B cross C. So it's the height on this area. So basically this is nothing but base times height, where the base is not a single line, the base is the area. So it gives you the volume of the rectangular parallelepiped. Okay. So the geometrical significance of the scalar triple product is the rectangular parallelepiped formed by the vectors A, B and C. And because of this, A dot B cross C is the same as B dot C cross A. See, if you take B dot C cross A, then C cross A is this area, this parallelogram here, right? And the normal is normal to this plane. So if you take the dot product of B with that normal, you get the height multiplied by this area, which again forms this parallelepiped. Similarly, C dot A cross B. A cross B is this parallelogram over here. Okay? So when you take the projection of C onto A cross B, then you are getting the base multiplied by the height. So same parallelepiped. So A dot B cross C, B dot C cross A, and C dot A cross B all have the same value, that is the volume of the parallelepiped formed by the vectors A, B, and C. Is this clear to everybody? Has everybody understood how we are getting the volume?
Yes, ma'am.
Yes. Okay. Not very
Yes,
difficult
ma'am.
to understand. You just need to visualize the three-dimensional picture. Okay. Other kind of triple product is the vector triple product, where of course you take the cross of all the three vectors, A cross B cross C. But here we cannot any longer write A cross B cross C equal to B cross C cross A equal to C cross A cross B, because each cross product will give you a different value. Okay. The only interesting thing that you need to remember is that of course this is, if you are given three vectors, you write the component form and you get the resultant vector by doing the determinant. Just note that suppose the three vectors are, say, x cap. Suppose you are taking the triple vector product of x cap and y cap. If you take it like this, x cap cross x cap cross y cap, then the result is 0, because we know x cap cross x cap is 0. On the other hand, if you just change the position of the parenthesis, if you just change the position of the bracket, and instead of x cross y, you take x cross y. What is the value of x cross y? Z. What is the value of x cross z? Minus y. So it is not 0. Okay. So when you are taking triple vector product, you need to be careful about the position, because the position of the bracket will change the result of the product. Just nothing very important, just you have to be careful when you are taking the vector product, whereas when you are taking the scalar product, the position does not really matter because the result is a scalar. Okay, so with all this information, we'll do a few sample numericals, very simple numericals based on what we have done till now. And these typical kinds of numericals might come in your objective portion. You have, usually your question paper contains 10 mark objective questions before the long answers begin. So these questions are typically of 2 marks each. So in this 2 mark section, you might get such small simple numericals from this portion. So the first one says, find a unit vector which is parallel to the resultant of these two given vectors, A and B. Okay. So what will you do? You will first find the resultant of the two vectors. It is given in a component form, so very easy to find the resultant. The resultant vector R is given by 3i cap plus 6j cap minus 2k cap. So this is the required unit vector. Okay. You find the resultant and then you find the unit vector along that direction. So very simple problem, but nevertheless a problem that might be given. Okay. This is a very important kind of problem. I want you to try this out first. I will give you about 3 minutes time, and I will again ask you after that. This is a typical very simple problem, but the result that we get is very significant. So I want you to try out first, and if someone is able to write R4 as a linear combination of R1, R2 and R3, you can unmute and tell me the result that you have got. Yes, has anyone solved already?
ম্যাম আমাকে কি এবিসি এর ভ্যালুটা বলতে হবে?
হ্যাঁ, এবিসি এর ভ্যালুটা বলবে।
এ এর ভ্যালু 3, বি এর ভ্যালু 2 এর 3 আর সি এর ভ্যালু 5 এর 4। আমার তো তাই
না,
হবে।
ফ্র্যাকশন তো আসবে না, ফ্র্যাকশন তো আসবে না।
সরি। ও এ আর 1 2 এ
Ma'am,
Ma'am, b
the
is equals
value
to
of A will
1.
be 0. The value of B
না
will be
না,
0 and
জিরো
C
না,
will be
না
1.
না 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 না, জিরো না।
Okay, okay.
Ma'am, b এর ভ্যালু কি 1 আসবে?
বি এর ভ্যালু 1।
ওকে।
এ দ্বিগুণ কর 2a যোগ b 2a যোগ b মাইনাস 2c ইকুয়াল টু 3। বি দ্বিগুণ কর মাইনাস বি বি দ্বিগুণ কর মাইনাস বি প্লাস।
বি ইজ 1, যে বি 1 পেলে সে বাকি এ আর সিটা বলে দাও।
ম্যাম করছি, ফার্স্টে বিটা আমি ইজিলি পেয়ে গেছি, এবার বাকিগুলো সলভ করছি। এই তো ম্যাম হয়ে।
Ma'am, A is equal to 0, B is equal to 1, and C is equal to -1.
নো, নো। Should I give the solution now? Because we have only 6 minutes left for the class.
Ma'am,
very,
C is equals to
huh.
-1.
Nah, C equal to -1.
But
Uh,
-3.
-3, yes.
okay, okay.
C is -3. B is 1, C is -3. For those who have not been able to start the
-2.
problem, -2. Yes, A is -2. So A is -2, B is 1, and C is -3. Very good for those who could do the problem. For those who could not, this is how you start it, okay? You are given 4 vectors and you are asked to write one vector in terms of the other. So first you write the 4 vectors in this form, okay? R4 is this 3i plus 2j plus 5k, and then A into R1, B into R2, and C into R3. Then in the next step, you gathered the coefficients of I cap, j cap, and k cap in this manner. Okay? And once you have the coefficients of I, j, and k on your right hand side, and you have 3 coefficients of I, j, and k on your left hand side, excuse me, all you need to do is equate the coefficients of I, j, and k from both sides. So these are the 3 equations that you get. You have 3 unknowns, a, b, and c, and you have 3 equations. So solve them simultaneously and get this result: a equal to -2, b equal to 1, c equal to -3. Okay, so very easy problem. And so you can write, I am sorry, the last portion of the vector is not showing. So basically you have written R4 as equal to -2R1 plus R2 minus 3R3. Now what does this mean? Remember our discussion on dependent and independent vectors? So since we have been able to write R4 in terms of R1, R2, and R3, therefore these 4 vectors form a set of dependent vectors. Okay, these 4 vectors form a set of dependent vectors. They are dependent on each other. If you would have got the simultaneous equations such that you would not be able to solve for A, B, and C, then the answer would be no, we cannot write R4 in this manner, and therefore they form a set of independent vectors. So this problem, simple but very significant, because it gives you a feeling of what I was talking about when I was talking about dependent and independent vectors. All right, next problem. Again, a very easy problem, but again, a very, very important type of problem. Find the angle between the vectors A equal to 2i plus 2j minus k and B equal to 6i minus 3j plus 2k. Okay. Do you want to try it out, or do I give the solution? This again is very simple. As I told you, you have to use both the formulae for dot product. So A dot B in the component form is this: AI AX BX plus AY BY plus AZ BZ. So you get A dot B equal to 4. Whereas if you take the angle formula, then AB cos theta is this, okay? √9 into √49. Magnitude of A is √9, magnitude of B is √49 into cos theta. So it gives you 21 cos theta. But both are A dot B, so you equate the two results, 4 equal to 21 cos theta, so that theta is cos inverse of 4 by 21. All right. And I did not bother to find out what cos inverse 4 by 21 is. You can use your calculators to do that. So if you are given to, so this is a very typical problem, very often given problem. 2 vectors are given, you are asked to find the angle between them. So you find the dot product once in component form and once in the angle form. Equate the two, get the angle. Okay? All right. problem. This again is a very important type of problem. Two vectors are given. You are asked to find the projection of A on B. Projection of one vector on another. So for this, the only thing that you need to remember is that you have to take the unit vector along the vector on which the projection is asked to be taken. So since you have been asked to take the projection of A on B, so you take the unit vector along B and get a dot product with A. Okay. Rest of the calculation is very simple and the answer is this 19 by 9. All right. Last sum for the day. Find a vector perpendicular to both I minus 3j plus 2k and 5i minus j minus 4k. Can someone tell me what do we do?
Ma'am, cross product.
Cross product. Yes, very easy. Vector perpendicular to both this is the cross product of the two vectors. So this is what the sum comes out to be and this is the result. Okay. And you can take a dot product of R individually with A and B to show, sometimes in the problem they ask you also that show that the result is perpendicular to both A and B. So you take the dot product of R with A and B separately to show that the result is 0, which shows that R is perpendicular to both A and B. Okay. So these are some typical sums. After this, we will have to go on to vector differentiation. What I will do is, since vector differentiation is a concept that you have not, these were all recapitulations, dot product and cross product also you did a little bit at least in school, but vector differentiation is a completely new topic. So we will start fresh with vector differentiation in our next class. In the meantime, I will give you a assignment, a very short assignment sheet containing sums on preliminary concepts, introductory concepts of vector and dot product and cross product. Okay, I'll upload the assignment both in the college website as well as I will post it in your WhatsApp group too. Okay, so you can go through the sums, do the sums, and I'm sure you will be able to do all of them. If you are not able to do one or two of them, then you can get back to me. All right, so with that, I'll end today's class.